Hello, we are Team Narvi from American High School in Fremont, California. This is our design review. Here's our table of contents. We'll be starting with our SMART requirements and then moving on to our concept of operation and system block diagram. After that, we'll cover our mass budget, the CAD model, our link and data budget and power budget, and then end with a review of our software and our integration and test plan.
These are our SMART requirements. The first requirement is that the CubeSat shall transmit a max of 14 images. We'll verify this by testing in orbit. Next, the CubeSat shall fit into a 1U length of 10 by 10 by 10 centimeters, and the CubeSat shall weigh 1.33 kilograms. This would be verified by measuring and weighing the CubeSat. The CubeSat shall take multiple images a day. We'll verify this by testing the camera. And the CubeSat shall distinguish between water and plastics. We'll verify this by testing software. The CubeSat shall cost close to the predicted bill of materials. This would be verified by checking the specific materials and seeing if they go over budget. The CubeSat shall take 10 minutes to transmit images, and it shall be in orbit for 92 minutes. These both would be verified by testing in orbit.
The concept of operations for our CubeSat is fairly simple. Once it's powered on and launched into orbit, we'll measure the initial orientation angle, which will be helpful in the later image analysis to allow us to calculate the exact location of the CubeSat when it was taking the picture. So in orbit, it will take pictures once it is facing the surface of the Earth and in daylight, and it'll repeat that process in set intervals of around 1 image per minute. We have to calculate that later using the data budget. And it'll start pre-processing the images when it's on the dark side of the planet in its orbit. And we'll do that to allow it to conserve energy and also help maximize the CubeSat's ability to temperature control and maintain heat in the cold on the dark side. So once it's in range of the ground station's connectivity, it'll connect and downlink the pictures it took along with the metadata, for example, the time and the orientation angle. And it will repeat that entire cycle in intervals across every orbit and continue until the power is depleted or we have to take it out of orbit. On the ground station itself, all systems will remain active and continuously receive data from the CubeSat, and it will be doing most of the heavy processing there. So whereas the CubeSat might have just determined which images were significant enough to send, the ground station is where it's going to detect the plastics and the type of plastics and then push that data to the web on GitHub.
System level block diagram. In our CubeSat, we have 7 subsystems, which are structure, power, imaging, command and data handling, communications, thermal, and ADCS. In the structure subsystem, we have solar panels and an acrylic chassis. For power, we have solar panels attached to the CubeSat, the Raspberry Pi power supply, and the batteries. For imaging, we have the Raspberry Pi camera. For command and data handling, we have the Raspberry Pi. For communications, we have the Bluetooth radio. For thermal, we have heaters. And for ADCS, we have the IMU. The arrows show how each of the subsystems are connected to each other. For instance, the solar panels attached to the CubeSat power the acrylic chassis and the solar panels, and the batteries help power the Raspberry Pi power supply, and the Raspberry Pi power supply helps power the Raspberry Pi. And this helps with all the other subsystems like imaging, thermals, ADCS, and communications. Mass budget and bill of materials. The products used to build our CubeSat was a Raspberry Pi, SD card, an IMU, a Raspberry Pi camera, etc. We used 22 items, and in total, this ended up costing $227.88. The total mass of all these products was 301.5 grams. The total possible mass of a CubeSat is 1,330 grams. Even with a 15% margin of error, our CubeSat mass would still be underneath this threshold. The Raspberry Pi would be the command and data handling subsystem. The IMU would be the ADCS subsystem. The Raspberry Pi camera would be the imaging subsystem, and the solar panel and battery would be the power subsystem. The acrylic panels and the acrylic side panels would both make up the structure subsystems.
This is our CAD model, and it consists of 5 main components. Our Raspberry Pi, which is our processing system, our IMU, which is used to detect the position of the CubeSat, and our battery pack. It is secured with 4 L brackets, and a panel is placed between separating the components so that if they are dislodged, they won't be able to cause damage to other components. These are different views of our CAD model, and here you can see our camera V2, which will be taking pictures that we can then use to detect macroplastics, and our solar panel, which will be used for energy collection and hooked up to our battery pack so that the battery pack can store that.
Here's our link budget. We assumed that our CubeSat would be orbiting in low Earth orbit, and we use the following parameters for low Earth orbit to calculate our link budget provided by the CubeSat course. We assumed an orbital height of 400 kilometers. That doesn't change. In a real-world scenario, this assumption would obviously not hold. Finding a more representative orbital height and analyzing its effect on the link budget are things that our group still needs to work on. However, using this given orbital height, we were able to calculate the shown values for the uplink center frequency, transmit power, antenna gain, and EIRP. Here's some more of our calculations. We found a free space path loss of 137 decibels, an uplink SNR of 29 decibels, and a downlink SNR or signal noise reduction of 21.3 decibels.
Okay, so for the power budget, we tried to figure out how many solar panels we'd need for the Pi to run when using the camera and how many we'd typically be using when it was idle. So the power produced per solar panel is 0.231, and then using the multimeter on a Raspberry Pi, we found that the Raspberry Pi uses 3.7 watt hours when idle, and when it's using the camera, it uses 7.4. So using this higher power, we got that we would need approximately 32 solar panels. And then in the table below, we actually just tried to find how much peak power would be used according to the specifics given online, just to compare what we measured versus what we should expect. And we actually got the peak power to be around 16.7 volts. So we will probably, in our design, try to have more than 32 solar panels just to account for this increased wattage. And as for the data budget, so the resolution of the images taken by the Raspberry Pi are 3280 by 2464. And since each one is 3 bytes, because of the 3 like RGB values, that would be 24 bits because each byte has 8 bits. And then we have the width and height based on the resolution itself. So then the image size ends up being 3 times 3280 times 2464, which is a very large number of bytes. And then if we include 4 bytes per image for metadata, like when the picture was taken and the location that the picture was taken, each image would end up being approximately 24 million bytes, more than that in fact. So we calculated our channel capacity using the formula given in the LLX course, and we got our channel capacity to be 4.48 megabits per second. And this is with our bandwidth being 1 megahertz and our downlink SNR, as Nandana said, to be 21.3 decibels. And with that channel capacity and our image size, we got that the time to transmit each image would be approximately 43.3 seconds. And with that, knowing that we have a total of 10 minutes to transmit all of our images, which is just 600 seconds, we got that we would be able to transmit 14 images. And while this number seems fairly small, we have included in our plan that to delete a lot of the images after pre-processing to see whether any objects of interest are even in the image.
The software architecture. So for the CubeSat itself, we have a simple process. Once it's powered on, we'll test the connection. If there's an error, rerun until it's able to connect to the ground station. And then starting orbit, it'll record the starting angle. It'll measure the displacement angle continuously while it's in orbit to determine if it's in daylight and if it's in a position to take pictures. If the displacement angle, the yaw, is equal to the set angle that we have to determine experimentally, it'll start capturing pictures with the function that we determined, take pic. It'll increment the number of pics we've taken, and we'll do a basic pre-processing function to determine if the image is significant. So that includes detecting maybe large objects, or just determining that the image is of the ocean and it's not empty and it's not blurry. Those are things which can be done on the CubeSat itself without using up too much processing power, while still being able to overall maximize the efficiency of our entire system. If the CubeSat determines the image to be significant, it'll downlink the image to the ground station later, and it will clear the images to conserve storage. Once we've achieved enough pictures in our orbit, we'll increment the number of orbits and continue that until the time has reached maximum. On the ground station, we'll be again testing the connection to the CubeSat, making sure that it's able to receive the images, including the metadata, and we'll make separate threads in our function to detect the plastic. So using a function that takes a picture in hue saturation value, which has been shown to be more beneficial in image processing. We'll increase the contours and use the OpenCV Python library to set a bounding box around the image and detect objects. We'll do the detection and then push the data and the images to GitHub in order to make it available to the cloud. And we'll make sure that's separate in a separate multi-thread so that we'll be able to accept any errors and keep the CubeSat able to connect to the ground station, even if we face errors with pushing data.
Here's our integration and test plan. Our immediate next step is to assemble our CubeSat. We understand that there's a risk of certain electronics interfering with others and risks associated with improper wiring. So these are things that we'll keep in mind during this process. We'll begin our testing by connecting the CubeSat to its ground station and ensuring that its subsystems are functional. Our testing will consist of activating our camera, capturing an image, compressing and transmitting it to the ground station. Once we view it and ensure that it's of the intended target and viewable, we'll record its location and begin conducting normal orbital cycles. We anticipate having to troubleshoot during this process and repeat these tests several times before we achieve our intended results. And with that, thank you so much for watching our design review.